All right. So you have already seen what is the matrix representation of any linear transformation, right? So given any linear transformation, we can do the matrix representation, right? So with respect to whatever basis you have. So this topic is clear for everyone, right? Matrix representation. Yes or no?
Um,
Are there any questions in this part, matrix representation? So I'm having a quick revision here if you want. So if you have
yes,
a linear
ma'am, please.
transformation T from V to W, okay, so let's say that, so if you are having n vectors in the basis of the vector space V, what is the dimension of V? What's the dimension of V in this case?
N.
Yes, the dimension of V is n. And what about the dimension of W? Because you see that gamma has m vectors as a basis for W. So what should be the dimension of W?
M.
M, right? So you are having a transformation from a vector space of dimension n to vector space of dimension m. Okay. So the matrix representation of T, okay, so let's, for example, let us say the matrix representation of T is this. What should be the size of this matrix first of all? This is n, this is m. N
M
represents
cross
n.
N.
It should be m cross m, right? So this is the first thing you should know about matrix representation. Okay, fine. Now you are having an m by n matrix, and how are we going to form the entries? So for that, what are we going to do? We are going to first find TVI for each of this I equal to 1 to n. And then we are going to express that as a linear combination of W1 to Wm. And these coefficients goes as the columns of the matrix. So here you see that the coefficients of TV1 in terms of in terms of WIs are given here, and the coefficients of TV2 in terms of WIs are here, and so on, right? So this is the matrix representation of a linear transformation. Okay, fine. Now let us do a problem which is given here in this way. So consider a linear transformation. So here, this is the vector space we are considering. Okay. So here you see that we are having matrix spaces as vector spaces. In the last session, you might have seen examples with Rn and Rm. So I thought maybe I can do some problem with matrices. Probably this was not done in the previous session. Is that correct? Or did you already have some examples of such type as well in the last session?
Ma'am, I didn't understand the last session, I feel.
Okay, no problem.
Really.
Okay, fine. No worries. So maybe I will do a simple problem first of all, and then I will move to this matrix example maybe. Okay. So maybe let's do something like T from R2 to R3. So what should be the size of our matrix?
3 cross 2.
Yes. Okay. Now let's take the very simple case of canonical basis. What is mean by this canonical basis or standard basis? We call standard basis is nothing but, so let's say the basis of R2 is
1
3. So what is the standard basis for R2?
1 0 0
R2. And what's the standard basis for R3?
1 0 0 0 0 1 0 0 0 1.
Okay. So this is the standard basis of R2 and R3. So now I want to express my T, the matrix of T with respect to these two bases. Okay. So what I have to do is that, so let us say my T of x comma y is 2x comma y plus z comma x plus y plus z. Okay. So suppose this is my T. Okay. So can you clearly see that the domain is from R2 and the codomain is in R3. Okay. So now how are we going to find the matrix? I'm going to write T of first 1 comma 0. So here, this is my V1. This is my V2. This is my W1. This is W2. And this is W3. Okay. Now I want to write my TV1. This is my TV1. Okay. In terms of W1, W2, W3. Okay. So first of all, what is TV1?
Two processing.
So T of 1 comma 0 is, can you tell? 2 comma, oh sorry, hold on, there is a mistake here. So here I don't have any Z, right? So there is an error in the way I have defined this transformation. Hold on. So let me make it like y plus or simply minus y, and then I have x plus y. Okay. Yeah, now it makes sense. Yeah, sorry. Yes, now T of 1 comma 0 should be
2, 0.
2 comma mine 0.
yeah, and then
1.
1. All right. What about T of 0 comma 1?
0 minus 1, 1.
0 minus 1 and 1. Right? So now you see that I want to express T of V1, which is this. This is my T of V1, 2, 0, 1 as a linear combination of W1, W2, W3. So if W1 is this and W2 is this and W3 is this, what should be the coefficients for this 2, 0, 1? Tell me the coefficients. It's very straightforward, right? It should be 2, 0 and 1.
Yes.
Yeah. Similarly, let's find, so now this is TV2. Now we have to write TV2 in terms of again W1, W2, W3. Exact same process. So now T of 0, comma 1. What are the coefficients again?
0 W1 minus 1 W2.
Minus 1.
Yes.
1 W3.
Yeah. 0 minus 1 and 1. Yeah. So now what are the entries of the matrix? So remember, see, always this is the first recommendation whenever I am teaching matrix matrix representation of a transformation. This is the first suggestion I tell. Always, okay, even if it is a very simple problem, first write this. Okay, so TV1, TV2 like this you write. So here example, you write like this. First write it in the top, so that you don't make mistake of writing the columns as rows. Many people, very often I have seen, they tend to write 2, 0, 1 as the first row and 0 minus 1, 1 as the second row. That is incorrect. So the first step, what you should do while doing this matrix representation is write TV1 and TV2 on the top, so that you know that TV1 should fall below this. So you should have the entries here and TV2 goes here. Is that clear? Now, what is the dimension of this matrix? Size of this matrix? You have a
3 by 2.
3 cross 2.
3 cross 2.
yeah. So the matrix representation, is it clear for everyone now? Yeah. Shall we proceed with the next example? Okay.
Yes, ma'am.
Okay. Now, instead of R2 and R3, I am having matrix spaces here. But the process is exactly same, nothing new. Okay. So here they are defining P of A is equal to PA. Okay. So this is the how they are defining the matrix transformation, where P is some specific matrix like this. Maybe if we want, let us say P is equal to 1, 2, minus 1 and 0, something like this. Okay, so let's take P to be this specific matrix. Now let beta be this matrix, be an ordered basis of M2 by 2 of R. So I did not take the options. I just want to compute. So I just simply skipped writing the options here. So let's try to write T, matrix of T, with respect to this basis for both domain and codomain. So let's first call this as V1, V2, V3, and V4. So always first you see what is given and then you see what you have to do. Now, what is it we need to do? We have to write TV1 as a linear combination of V1, V2, V3, and V4. Similarly, TV2 as a linear combination of V1, V2, V3, and V4. And TV3 again as a linear combination of V1, V2, V3, and V4. TV4 as a linear combination of V1, V2, V3, V4. Now, how are we going to find TV1, TV2, and so on? So, for TV1, what is the formula given to us? It is V1 times of A. Sorry, this P times of V1. So what is this P? Our P, we have considered it as 1, 2, minus 1, 0. So 1, 2, minus 1, 0 into what is our V1? 1, 0, 0, 0. So you do this matrix multiplication. Similarly, do the matrix multiplication for all the matrices. And when I ask, you give the answer. Now, everyone take your paper and pen. Do this matrix multiplication and tell me the answers. When I ask, not now. Because let everyone try. I will give few minutes for everyone to complete this step. And then when I ask, you can start giving your answers. See here, what is that we did? We are just doing T times of B is equal to PV. This is the definition, or T times of A. So here A is V1, here A is V2, V3 and V4. Shall we look at the answers? Did all of you get enough time to complete? Shall we look at the answers?
Yes, ma'am.
Okay,
Yes, ma'am.
fine. So what is TV1?
1 0 minus 1 0.
1,
1 0 minus 1 0.
and what is TV2?
0 1 0 minus
0 1 0 minus 1.
0, 1, 0, minus 1. Okay, what about this?
Ma'am, it's
Ma'am,
0 1 0 minus
0
1.
1 in the
Yes,
first row.
yeah, yeah. And then what is TV3?
2 0.
2 0 minus 1 0.
2 0 0
Okay.
0.
And here
0.
Ma'am, I got 0.
0 and again 0.
Yes,
Right? Now what are we going to do? We are going to express this as a linear combination of V1, V2, V3 and V4. So remember what is your V1, V2? This is your V1, V2, V3. So V1, V2, V3, V4. So it is very straightforward again because this is the standard basis again. So what are the coefficients? 1,
1 0
oh sorry, 0,
minus 1
minus 1,
0.
0. Okay. So you have 1. Let me write the answers here so that we can write the matrix directly. So you have 1 minus
Ma'am,
1. Yes.
ma'am, in TV3, in second row, first column, it's 0. Instead of minus 1, it's 0.
yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Here.
No, ma'am, in TV3.
Okay.
Also, ma'am, in
Instead of minus 1, it's 0.
1 2 1.
TV4 should be 0 to 0 0.
it is actually 0 to 0. Others are 0, ma'am. Ma'am, and then TV4 is 0 to 0 0.
Okay. So let me do the calculations myself. So you have the first in this is correct. So you are saying here. Okay. Let me check that as well. Okay. So this is 0. Quickly, I should have checked. So here it is 2 on the other side.
They actually
0 and 0.
1 0.
All right. So now let's write the coefficients quickly. So the second one, the coefficients are 0, 1, 0, minus 1. Right? And then here 2, 0, 0, 0. And here 0 to 0, 0. So remember, for writing the matrix, always first write TV1, TV2, TV3, TV4, and then you write the matrix. So what's the first column? 1,
1 0 minus 1 0.
and here
0 1 0 minus 1. 2 triple 0.
0 2 0 0.
So you notice that here the matrix is of order 4 by 4 because both of these are of dimension 4. All right, clear? Okay,
Yes, ma'am.
all right, good. Now, so in this example, we have taken the same basis for both domain and codomain. Now we are having a different setting. Now we are having, let's say you are both the domain and codomain are same, but the basis we are going to consider are different. Okay, now we have two different bases for the same domain and codomain. Now, if ABCD is a matrix representation of the linear transformation with respect to beta for both the domain and the codomain, we have to answer these following questions. What is the matrix representation of T with respect to gamma for both the domain and codomain? So, how are we going to do this? Okay, so first we should understand, maybe here also let's take a simple example to have a better visualization. Let's call this matrix as maybe 1 0 minus 1 and 2, and we'll do this. Okay, so let's call this.
Whatever you want, we can take this matrix.
No. See, we are doing this parameterization, right? So I have taken that question from there directly. So for each of you students, you will be getting different matrices here actually.
Okay.
So here V1, V2, W1, W2. So these are like fixed values. You cannot take random values. You in exams you will get some matrix like this, not like this. Okay.
Yes.
So forget about this. So this is the matrix you are given. Okay.
So, ma'am,
Now
in place of that, we will get a matrix A in place of ABCD matrix, right?
exactly.
Okay.
Okay. So what is given to you? It is given that this is the matrix representation of T with respect to beta for both the domain and codomain. So from this, what we can say, this is TV1 in terms of V1, V2, and this is TV2 in terms of V1 and V2. So let's first understand what is our T so that we can further proceed. So we are given that TV1 is 1V1 minus 1V2. So what is TV1 actually? Compute and tell me.
T10.
What is TV1 actually? What is the vector? 1V1 minus 1V2. Is it that difficult to calculate? 1V1 minus 1V2. So what is this vector?
1 minus 1.
Yeah. So this is the
1
vector.
1.
1 minus 1.
Yeah. Similarly, TV2 is 0V1 plus 2V2. So it is
0, comma 2.
simply 0 comma.
Ma'am, how it is 1 V1 minus 2 V2?
That is how we are, you remember, that is how we are doing this matrix representation. So TV1 is A11 W1 plus A21 W2 and so on.
Okay.
Okay, now we are doing the reverse. So we usually go from this to this. Now we are having the matrix, and from matrix we are going back to this. Okay. Now from here,
Ma'am, both questions can be asked in the exam, right?
yeah, maybe yes. Any kind of questions are
Ma'am,
possible.
how, ma'am, can you elaborate, ma'am, this how we are going from matrix to this? I did. First
See, that
example was clear.
exact same procedure. See, now we are given this matrix and we are asked to find what is TV1, TV2, TVN. Okay. So now what is that we know is that the information given to you is that TV1 See, the information is given here. This matrix is the representation of T with respect to beta. Beta is V1, V2. With respect to V1, V2 for both the domain and codomain. It means what? It means what? What does this mean? Let me tell. So this part, so matrix of T with respect to beta for both domain and codomain. So this means exactly this. So TV1 is AV1 plus CV2 and TV2 is BV1 plus DV2. This is the meaning of this. Okay? Whatever is the matrix, this is the meaning.
Ma'am, where are W1 and W2?
Here in this case, that is the difference I told you in the first, before even starting the problem, that's what I told. Here, we are not considering W1, W2. It is given that we are considering beta for both the domain and the codomain. In the previous
Okay.
case, we had different bases, beta for the domain and gamma for the codomain. That's why we took the elements of gamma, which are W1, W2, Wm. Now we are considering beta for both the domain and codomain.
Okay, understood, ma'am. Thank you.
Okay. Now, from this, is it possible to tell what is T of x comma y? T of x comma y. Okay. First, one thing. This is a basis, right? If this is a basis, can we express any vector in R2 as a linear combination of these two vectors?
Yeah.
Okay. So, in that case, how can you express x comma y as a linear combination of V1 and V2?
X into
1,
0 plus
So, xv1 plus
y v2.
yv2. Now, if I'm applying t, so you know that x and y are just scalars. X and y are just real numbers, right? So it means that what happens? You have x tv1 plus y tv2. So what is tv1? Have we already computed tv1? Yeah.
Yes, 1 minus 1.
And tv2 is?
0 2.
Okay. So now do we have the t of x comma y? Simplify this and tell me.
X and minus x plus 2y.
Okay. So you have t of x comma y is equal to x comma minus x plus 2y. So first we have understood what is our transformation from the given information. Okay. So we have understood what is the matrix, what is the transformation from the given information. Everyone listen very carefully. I am going to give you a small hint here. So listen carefully. If the domain, if the base is considered for domain as well as codomain, are both the standard basis. In this case, you note that this is the standard basis. Okay. If it is a standard basis, you have a shortcut. If it is not the standard basis, this is the process you have to go through. First, you have to write TV1 as a linear combination of the basis elements given for codomain and TV2 as a linear combination of the basis elements of codomain. And then you have to calculate T of x comma y like this. But if you are given the standard basis as the basis for both domain and codomain, like in this specific case, there is a shortcut. What is the shortcut? Shall we see? First of all, do you understand what I'm going to say? Is that part clear?
Yeah.
How to compute T of x comma y without doing this process if both the domain and codomain are using standard basis. Okay. So for that, you see that it's very straightforward. T of x comma y is nothing but 1, 0, minus 1, 2, x, y. Everyone calculate and tell me what is the vector you are getting.
Ma'am, same.
Yes.
X and minus x plus 2y.
Remember, this is applicable. This
Only with standard basis.
yeah, Tx is equal to Ax only when A is represented with standard basis for both domain and codomain. Remember this. Otherwise, you cannot apply this. Okay, is that clear so far? Okay, fine. Now let's proceed. Yeah. Yes. What's your question?
Ma'am, I have a question.
Yeah.
Is there any trick for like if we have the standard basis of R2 for domain and a standard basis of R3 for codomain? Is there any trick for that as well?
Exactly the same trick only. Only thing is that, see, so,
Yes.
okay, for example, here you have this matrix, let's say, you don't know what is the transformation. Okay, now here you know that this is from, T is from R2 to R3. Okay, so here the same exact same trick will follow. So you see that T of x comma y is a times of xy. So you do a times of xy and see what is it you are getting. Try it and tell me right now. 2x.
2xy,
No,
2xz, sorry, 2xz and
there is
comma
no z. Come on,
minus
rewrite
yz.
it. Okay, hold on. Let me write it. I guess you are making some errors because I'm not writing. I guess maybe I'll write it specifically. Now tell me. It's
2x
2xz, z
and
there
minus
is
y.
no z.
minus
Where is z
y.
here? There is no z here.
Oh, yes, ma'am, sorry.
2x and then
Minus y.
minus y,
Minus y,
x
X
plus y.
y.
x plus y.
this is the exact same transformation we are having. Okay, so the same technique will work if we are using the standard basis for both domain and codomain. Okay,
Thank you so much, ma'am.
all right. Okay, so now the next step we will move. The next step is that what is the matrix representation of T with respect to gamma? So gamma is this with respect for both domain and codomain. So it means what? What is that we need to do? We need to find TW1 and express it as a linear combination of W1 and W2. And similarly, find TW2 and express it as a linear combination of W1 and W2. Remember, now gamma for both domain and codomain. That's why here also W1, W1, W2, here also the same. Okay, and then we have to write TW1, TW2 as the matrix. Okay, so now everyone find TW1 and TW2. So it means you have to find what is T of 1 comma 1 here and T of 1 comma minus 1 from this which you have already computed. What is T of 1 comma 1?
1 1.
1?
Minus 1.
1
1.
minus 1.
No, it's
No, ma'am. 1.
1 only, right? Minus 1 plus 2 is
Yes,
1.
ma'am. 1.
Yeah. And what is T of 1 comma minus 1?
1 minus 3.
1 minus
1
Minus 3, ma'am.
minus
3.
Minus 3.
Yeah. So this is the first step. Now the next step is that we want to express this 1, 1 as a linear combination of W1 and W2. So how are we going to do that? 1, 1 as a linear, you don't know what are these entries, right? So maybe let's call them as alpha 1, 1, alpha 1, 2, alpha 2, 1, and alpha 2, 2. So here it should be alpha 1, 1, and then alpha 2, 1, and then here alpha 1, 2, and alpha 2, 2. So 1, 1 as a linear combination of these two. So alpha 1, 1 times of, what is W1? W1 is 1, 1. And W2 is 1
1
minus
minus
1.
3.
No, W2 is just 1 minus 1, right? So this is your W1, W2, remember?
Yes, ma'am.
Now, what should be the coefficient? This one is a very straightforward equation.
Then 1
From
and
this,
0.
alpha 1, 1 should be 1 and alpha 2, 1 should be
0.
0, right? All right, okay. Now, what about the next alpha, not 1 comma minus 1, 1 comma minus 3, right? Yeah. 1 comma minus 3. What about this? Now we have alpha 1 2 times of 1 comma 1 plus alpha 2 2 times of 1 comma minus 1. Now here what should be alpha 1 2 and alpha 2 2? Are you able to make a guess or should we solve the system of linear equations?
Ma'am, I have solved it -1.
Sorry, what?
Alpha 1 is -1.
Alpha 1 2 is -1. Okay. And alpha 2 2 is
2. This is 2.
2. So you see that 1 minus 2 is okay. Here -1 plus 2 is 1, and then here again -1 minus 2 is -3. Yeah, it works. Okay. So here, so the matrix we should have here is, so let's call this the matrix with respect to gamma is 1 0 -1 2. So is this clear for everyone? Yes or no? Up to this, is it clear? Yes. Any question?
Yes, ma'am. Yes, ma'am.
Someone has raised your hands. Yes. What's your question? Okay, then I'll continue. Okay. What is the, so now we have seen matrix representation of T with respect to beta for both domain and codomain, and then gamma for both domain and codomain. Now, what is the matrix of T with respect to gamma for domain and beta for codomain? Remember, gamma has elements W1, W2, and beta has elements V1, V2. Now, I want you to think for a moment and then answer what is that we need to do. First, think it in your mind and then tell me. What is that we need to do?
Ma'am, we need to find out TW1 and TW2.
Yes,
And then the linear combination of V1 and V2.
exactly. We need to write them as linear combinations of V1 and V2. Very good. Okay, because gamma is for domain and beta is for codomain. Okay, so everyone try to compute it by yourself. I will give you 3 minutes to complete this, and then when I ask, give your answers. Everyone try to complete this part by yourself. Let's see whether you have understood this matrix representation clearly. Shall we check the answer? Yes.
Yes, ma'am.
You
Yes,
can
ma'am.
yes, you can try the answer. So what are the coefficients of V1, V2 for TW1?
1, 1.
1, 1. Very good. What about TW2?
1 minus 1.
1 minus 3, ma'am.
Minus 3. Correct. Okay. So for domain gamma and codomain beta, we have 1, 1, 1 minus 3.
Ma'am, could
Remember?
you please explain the minus 3 part?
Okay. So here, first of all, what is TW2? We have already computed TW2, which is 1 comma minus 3. Right? So obviously,
Okay, got it, ma'am. Thank you.
yeah. Clear?
Ma'am, could you explain this problem?
See, it's very straightforward. See, TW1 is what 1 comma 1. 1 comma 1 in terms of the standard basis, you know that 1v1 plus 1v2. Right? So the first column is 1, 1. We are expressing, so remember here for domain, so for it's given that for domain we are considering gamma. Gamma for domain. So we are considering W1, W2 here. And for codomain, we are considering beta. So that's why we are considering V1 and V2 here.
Ma'am, we have already found that transformation matrix by shortcut.
We have already computed the transformation. So this is transformation. Here, the domain, the basis we have considered is beta for domain and codomain. And then in the second scenario, we considered gamma for both domain and codomain. Now we are considering gamma for domain and beta for codomain.
Ma'am, how we know TW1 like transformation TW1 and
See,
TW2?
here the main transformation is given by this. So this is the actual transformation which does not have to do anything with whatever is the basis we are considering for the matrix. So this is the original transformation we have found. So you can compute TW1 and W2 from here. So W1 and W2 are given by these vectors. You just substitute them here and compute it. That process we have already completed. So here we don't have to compute straight away. You take the values here and do it. Got it?
Ma'am, we can do find the transformation matrix by first method is shortcut if the standard bases are there,
Yes.
and if standard basis is not there, then what is the way, ma'am?
If standard basis is not there, then this is the way. This is how we are finding the matrix or the transformation.
Okay, okay, using this alpha 1 1. Okay.
Yeah, yeah, yeah. Okay. So here is a homework for everyone to see whether your understanding is good enough. So the homework is find matrix of T with respect to beta for domain and gamma for codomain. Try this just to check your understanding. Okay. Can you all try this homework? All right. So let's move on. Okay. We have already seen what are null space. Yes.
Actually, if first and the second question wasn't given, directly the third one was given, then we have to calculate the whole thing,
Yes. Yes. Yes.
even if it weren't there, right?
Yes. Correct.
Okay, thank you, ma'am.
Yeah. All right. See, if this question was asked directly, then you would have first did this one. You would have first found T of x comma y. You would have did this step and then did this. That's all. Okay. Fine.
Got it, ma'am. Thank you so much.
Yeah. So what is null space or the kernel? So the null space, if you have a matrix, what is a null space? If you have a matrix A, what is the null space? So null space of A is set of all x such that Ax is equal to 0. The solutions of the homogeneous system Ax equal to 0. Now, similarly, the kernel of T or the null space of the linear transformation is simply the set of all V in V, the domain, and TV such that TV equal to 0. Note that kernel is a subspace of the domain V. Okay, remember kernel is a subspace of the domain. Now, what about the image or range space of a linear transformation? If T from V to W is a linear transformation, we define image of T denoted by image of Im of T as follows. Set of all W in small w in capital W. So that is set of all the elements in codomain such that there exist. So maybe a picture is better in this way instead of just reading out. So this is your V, this is your W. Okay. So let's say that you have some elements here. You have actually infinitely many if it is a vector space. Just for visualization, I'm saying. Okay, let's say that you are having the mappings like this. Okay, so all these things are coming here, 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 like this. Now, all the points where you are having the images mapped, so this particular set, we are calling it as image of T. Okay, so it means what? You are considering all W such that for each W here, you should be able to find a V such that TV equal to W. Okay, such W's are called the elements in the image of T. Okay, so suppose you have some W outside, okay, and you are not able to find any pre-image, then this is not in the image. Only elements for which you can find a pre-image, you have a W. You call it as a element in the range. Okay, so here this V is called the pre-image of W. What do we call V for W? Here we call V as the V is the pre-image of W under T. And W is the, can you complete? Dash of,
Image.
yes, image of
Post image.
V.
under T. Okay, just some terminologies to read this correctly. So all this W for which you have a pre-image in V, they are called the elements in the range. Okay, so we can see that range and null space both are subspaces. Okay, so range and null space both are null subspaces. I guess in the last session you have already completed the null space part. Am I correct? In the previous session? Yes or no? No one remembers?
Yes, we did it.
Yeah, thanks. At least one is able to remember. So you see that null space is a vector subspace. Similarly, we can also see that range space is a vector subspace. So first of all, for a vector subspace, what is the condition we need to verify to say that a given set is a subspace? What is the condition?
The zero vector.
Zero vector should be there, but for subspace usually there is a condition which we check. What is that?
Addition and multiplication, scalar multiplication.
Yeah, so it should be closed under addition and scalar multiplication, right? So suppose you say that S is a subset of V. Okay, how to prove S is a subspace? To prove that S is a subspace of V, what do? We take two elements, S1, S2 in S, right? And we take alpha S1 plus beta S2 and say that alpha S1 plus beta S2 is also in S. Then we say that S is a subspace. This is what we do. Okay. So can we try this for this set here? So here we are having the image set. So now can we try this for the image set? How can we do this for the image set? So it means we have to take two elements. So since it is in W, maybe we'll use this notation, W1 and W2. So yeah, here the other thing I wanted to say is that kernel is a subspace of V and image is a subspace of W.
W.
Okay. So image of T. Now we want to say that W1 alpha times of W2 plus beta times of W alpha W1 plus beta W2 also belongs to W image of T. Okay. First of all, if W1 and W2 belongs to image of T, what does the definition say?
W1 plus W2 belongs to image of T.
There exists, according to the definition of image, there exists V1, V2 in V such that, can you complete?
V1 and V2 are the pre-image of
TV1 equal to W1 and TV2 equal to W2. Yeah, this is the definition of image. Yes or no? Right? Now, what can we say about alpha W1 plus beta W2? Now, alpha W1 is alpha TV1 plus beta TV2. Instead of W1, I'm writing TV1, and instead of W2, I'm writing TV2. Now, this is nothing but T times of alpha V1 plus beta V2, because by using the linearity of T, I have written this step. So, this means what? Alpha V1 plus beta V2. You know that V1 and V2 belongs to V, and V is a vector space. So, this also belongs to V. And this is a pre-image of this. So, image of T is a subspace of W. Is that clear? Is that clear for everyone? Yes or no?
yes, ma'am.
All right. Okay. So now, since they are subspaces, now for any subspace, you know that we can define dimension. So the dimension of the kernel or the null space is called the nullity, and the dimension or of the image or range is called the rank. Okay, fine. So already you might have seen the terminology of rank in terms of matrices. Can you say what is mean by rank of a matrix?
Number of non-zero rows is the RRE of matrix.
Yes. Okay. Or you can also say number of linearly independent rows or columns of the matrix. You can say in that way also, yes or no?
Yes.
Yes. Right. So there is some very important relation you should know about. What is according to this definition, what you have, and what is that you have for the rank of it. Okay. So range or the image, okay, can also be considered as set of all TV V in V. So this is another way of writing the same. Okay, set of all TV where small v belongs to V. So this is another way of writing. What does this mean? How can we understand this? So just I want you to understand this part. So maybe if I have some space somewhere else, I want to explain this because it's crucial in understanding the relation between the matrix and linear transformation. We'll do it somewhere at the end. Yeah, here maybe. Yes, this is better place. Okay. So let's say you have, maybe I will take a very simple scenario. Okay. So maybe I will take V to W. Okay. And you have TV equal. So A be the representation of matrix of T. Maybe I will take RM and RN here. Matrix of T with respect to standard basis for both domain and codomain. So if we have this condition, then what do we know about the relation between any vector? Let's say x is any vector in Rn. What do we know about Tx and Ax? They are equal. Tx is nothing but Ax. Yes or no? Are you all there?
Yes, ma'am.
Yes, ma'am.
Okay. So now, for simplicity, I will take simply maybe a, okay. So now, first of all, what is the size of this matrix?
M cross N.
M cross M.
Okay.
M by N.
Yeah. So now for simplicity, maybe I will consider something like this, R3 to R2, something like this. Okay. So the matrix should have 2 rows and 3 columns, right? M by N. So let's say that A11, A12, A13, A21, A22, A23. Okay. Now, what is mean by AX? What is mean by AX? So AX is nothing but this matrix. So maybe I'll write AX here itself so that I don't have to repeat writing A again. So let's say this is X and X2. Yeah. So now let's first split it and write it. So how can we write? A11X1. Oh, sorry. Here R3, right? So I need another. So X1, X2, X3. A11X1 plus A12X2 plus A13X3. And then A21X1 plus A22X2 plus A23X3. Is this fine? I have just did the matrix multiplication. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. Now I'm just going to rearrange and write it in the following way and see if it makes sense. I'm going to write it in this way. I can write it like this. Yes or no? Yeah. I have just splitted it and written it in this way. Okay. So what is that you observe here? So the observation is that this is your column 1, column 2, column 3. So this is column 1, column 2, column 3. So what I have done, AX, I have written it as a linear combination of columns of
X1, X2.
A.
C1, C2, C3.
Yeah, so here instead of C1, C2, yeah, C1, C2, C3 are the columns. So here I'm writing in general, linear combination of in general for any A, okay, for M by N also, AX always represents the linear combination of columns of A. Okay, so now, okay, now what is image of T? Other definition, the second definition I told, set of all Tx such that X is in the DOM. Let's say Rn in this case. Okay, so this means I'm considering span of, can I say, if I'm, so if Tx where X is in Rn, what does it mean? All possible linear combination of columns of A. Is that correct? All possible linear combination of columns of A. Is that correct?
Because tx is equal to ax.
Because X is varying in Rn. Here only one X I considered, so it is one linear combination of columns of A. Now I'm going to take all possible X's in Rn. So it means that I'm going to consider all possible linear combination of the columns of A. Is that making sense?
No, ma'am. Because tx is equal to ax, that is why you are concluding that.
Yeah. Because Tx is equal to Ax. Yes.
if we are not given Tx equal to x, can't we conclude that?
We cannot conclude that, but it is always possible for Rn to Rm. We have a standard basis, and always we can find the matrix A, and hence this is possible. So here I am trying to explain the relation between the matrix and the image of T. Okay, so how to understand it from the perspective of matrix, I want to say, that's why I'm telling this. So this I can, all possible linear combination, there is another name for it. Can you recall what is that? This word can be replaced with?
Column space.
Yes. So you are replacing this entire line, which is column space.
Span.
Yes. So this is what you earlier said is also correct. That is the final result. So span of columns of A, which is nothing but the column space of A. Okay. So this is a relation, crucial relation you should know. Where here, remember, A is the matrix of T with respect to standard basis for both domain and codomain. Okay, so this is some important relation you should all know. Okay.
Maybe bases are not standard, then Tx is not equal to Ax.
No, need not be.
Need not be.
Yeah. Usually it is not.
Okay.
Okay. Fine. All right. So coming back to this definitions here. So yeah, we have seen the relation between the image and image of T and the columns of A. Okay, so the image of T is basically the column space of A. So you can easily see that rank of T is same as rank of A, right? So now do you see that rank of T should be same as rank of A, because image of T is nothing but the column space of A, and the column space of A, the dimension of the column space is also the rank, right? Yeah. So rank
Yes,
of T is rank of A. Okay, good. Okay. Now let's look at this specific problem. Now there are 4 different options. Let's see how to understand them. There exists a linear transformation T from R to, I'm going very slow, I feel. Is it fine, or if you find it very slow, please let
No,
me.
ma'am. No, ma'am.
No,
Like
ma'am, it
topic
is
is very
absolutely okay.
abstract topic, ma'am.
Okay, okay, fine. Yeah. There exists a linear transformation T from R2 to R2 whose range is contained in the circle x squared plus y squared equal to 1. Okay, fine. So first we'll see what is mean by this x squared plus y squared equal to 1. Okay, so you have, this is R2. In R2, what does it mean by x squared plus y squared equal to 1? So if this is 1, this is 1, this is minus 1, this is minus 1. I'm not very good at drawing figures, so I'll try to draw a circle. If it does not look like circle, I hope you will understand what I'm trying to draw. Okay, so this represents x square plus y square equal to 1. Okay, so this is the circle. Okay, only this boundary, not the things inside. Okay, just this outer circle. Okay, now they are asking, there exists a linear transformation. Yeah. Okay, whose range is contained in this circle, they are saying. First of all, what do you know about the range? The range is a, here the main fact you need to use is that range is a
image.
Circumference.
range is a subspace of R2. Right? Here T is from R2 to R2. Here range is a subspace of R2. So what are the possible subspaces of R2? Either it should be origin or
Line passing through origin.
it is a straight line through origin, or it is the entire R2. So these are the only possible subspaces for R2. Now we know that range is a subspace. Okay. So if it is a subspace, first of all, the first thing you should know is that always 0, comma 0 belongs to range. That is the first thing you should see. And then second, check if it is any one of this. If first condition is satisfied, then go to the second. If it does not satisfy the first condition, you can stop right there itself. So second, see if it matches with any one of this. So maybe 1, 2, or maybe A, B, C. So it should be A or B or C. Okay. So in that case, so now here, first of all, does it contain 0, 0? You put 0,
No,
0.
ma'am.
Yeah,
Yes.
No,
0
ma'am.
square plus 0 square is not 1. So 0, 0 does not contain does not belong to this circle. So in this case, what do you say about this statement? Is it possible?
No, ma'am. False.
Okay, good. Now the second statement, there exists a linear transformation T from R2 to R2 whose range is equal to the line x is equal to y. Now what do you say? X is equal to y, does it fall under any? First of all, the first condition, check this condition. Does the first condition get satisfied in this case?
Yes, ma'am.
Yes, ma'am.
Okay. What about the second condition? Is it coming under any one of this category?
Yes, ma'am.
Yes,
Straight
it's
line
the
through 0,
straight
0.
line.
It is a straight line through origin. Okay. Now, just this is actually enough, but just to have a better understanding, can you try what should be the transformation whose range is exactly x is equal to y? Can you try what should be the transformation? T of x comma y. Your y should be
X, comma Y.
simply x.
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 एक एक प्लेट में
Both of them should be the same.
x equal to y. So
Since it is x equals to y, right?
Yeah, because you have x is equal to y, I have substituted y with x here. Okay, or you can put y comma y. Okay, so basically both of the coordinates should be same. That's what we have. Okay, so here you have t of x comma y mapped to x comma x. So you see that this is a linear transformation, and here the range of t is same as the line yx is equal to y. Set of all x comma x, so that x is in R, which is the line x is equal to y. Okay, so the second option is true. Okay, now what about the third option?
Not
There
correct.
is a linear transformation whose range is contained in the set where x is strictly greater than 0. So what
No,
happens to
ma'am,
the
false.
function? Okay, the 0 comma 0 does not belong. So this is for option 3. This is for option 1. So this you can see that this does not belong to S. So you can say that this is not a linear transformation. What about this?
Yes, ma'am.
0, 0 is possible, ma'am.
Yes, ma'am.
Yeah. Okay. In fact, what can be the transformation? Can you try?
Uh,
X,
pi
comma
x.
X comma pi x.
Okay.
x
Very
x
good.
to x.
Very good. I see you people are becoming experts now. Okay, good. Very good. Okay. So now we are going to see some examples with isomorphism. So can we quickly recall what is an isomorphism? Can anyone tell what is an isomorphism?
One and on. Both one and on.
Okay. So quickly recalling isomorphism. So let's say T is from V to W. Okay. So for one to one, what is the condition we need? In terms of the null space, can anyone say?
No.
Null space should be 0.
Null of T should be singleton 0. Okay. Are any other conditions equivalent condition? Tx is equal to Ty implies
X equals to Y.
X is equal to Y. Okay. What about onto in terms of range?
Range is equals to codomain.
Yes, is equal to codomain. Okay. What about isomorphism? That is 1 to 1 and on to. So first of all, it means that both these conditions should be there. So in that case, what can you say about dimension of V and dimension of W?
Same.
Same. Can anyone say what is the theorem behind this? From where do we get this? So here, for in 1 to 1 case, we know that nullity is 0. And in the case of on to, we know that rank is equal to dimension of W. And what does rank nullity theorem tells you?
Rank plus nullity is equal to number of columns.
In terms of transformation, rank of T, here we only have transformation, we don't have a matrix. So rank plus nullity is equal to dimension of V, right? Number of columns is same as the dimension of V, right? So now you see that now we'll substitute here rank is dimension of W and nullity is 0 if it is both 1 to 1 and on to, and on the right hand side we have dimension of V. So now you see why dimension of V is same as dimension of W if we have both 1 to 1 and on to. Is that clear? All right.
Yes, ma'am.
Yes, ma'am.
Okay, fine. Now, which of the following linear transformations is an isomorphism between the vector spaces V and W? So this means what? So here you are having V is this vector space and W is this vector space. First of all, can there be an isomorphism between these two? So it means first we need to look at the dimension of these two vector spaces. How do you calculate the dimension of these two subspaces of R3? I don't know whether I took this session, but you should all know how to find a basis if you have a set like this. What is the
Yes.
procedure to find a basis?
Let's substitute
Variables.
X. Substitute
Yes.
Y minus Z for X.
Very good, very good. Right? So for V, this is the procedure we can do. So you take Y commonly, and then you take 1, 1, 0, and then you take Z commonly, and then you have minus 1, 0, 1. You have two elements in the basis. So you have dimension of V is equal to 2. Okay. Similarly, can you now say for W?
And dimension is 2 for W.
So you have again X, X, and Z. Yeah. So again, you have dimension is 2 for W as well. Very good. So what can you say about option 4?
Wrong.
Wrong. Why is it wrong? If two vector spaces of same dimension are there, how to construct an isomorphism? Have you already seen this part? Let us see. Okay, fine.
No, ma'am.
Okay. So let us say you are having two different vector spaces. V and W are different vector spaces. Okay. Now, let's say dimension of V is equal to dimension of W. Now, how can we form a isomorphism between these two? Okay, take any basis of V. Okay, so let's say that the dimensions are some K. So V1, V2 up to Vk. And take any basis of W. W1, W2, Wk. any basis. Okay. Now you define TVI is equal to TWI. Sorry, TVI equal to just WI. Okay. For I between 1 to K. Now this T is an isomorphism. Okay. So isomorphism means 1 to 1 and on to conditions need to be there. I leave that verification part to you. So this is how you construct an isomorphism between vector spaces of same dimension. So whenever you have vector spaces of same dimension, an isomorphism is always possible in this way. Okay. So now can you answer this question? The option 4. Where is this? Yeah. What do you say about option 4 here?
False, ma'am.
Yeah. Okay. Fine. Now we will look at this one. T of x comma y comma z is equal to y comma y comma 0. Now for an isomorphism, you need both 1 to 1 and on to. Okay. So now for option 1, is it 1 to 1 and on to? So for 1 to 1, what is that you have? You need only the 0 vector in the kernel, the null space, right? But here, is it not very obvious that the kernel is not just 0, 0? Can you say a vector? Can you find a vector, non-zero vector, such that T of that non-zero vector is all 0, 0, 0?
Yes, ma'am.
Yes, what's the vector?
Suppose 1, 0, 2.
Yeah. In this case, y is 0 here. So you will get 0, 0, 0. So this means your kernel is non-zero. If kernel is non-zero, T is not 1 to 1. If it is not 1 to 1, it is not an isomorphism. Yeah.
Ma'am, how kernel is non-zero, ma'am? I forgot what is kernel, ma'am.
Kernel is the set of all vectors in V such that T V equal to 0. Now I have found a vector V such that T V equal to 0 and this V is non-zero. So
Ma'am,
hence,
how V is non-zero?
obviously you have non-zero entries in this vector, right?
V is non-zero.
Yeah, this is your V.
Okay. This is one into T into that should be 0, 0, 0, 4.
Yeah, TV is 0, 0, 0.
If we multiply by T, then how it is coming out as 0? T is a matrix, no?
T is a transformation. T of x comma y comma z is y comma y comma 0. X is 1, y is 0, and z is...
Okay, fine. Yeah, 0, 0. Yes.
Okay, so this is not an isomorphism. All right. What about option 2? What about option 2?
Also, no, wrong option, ma'am.
Okay, why is this the wrong option?
If we take, means it is not on to, so that's why.
Okay, why is it not onto? First of all, onto means you need to show that image of T is same as W, right? So it means here, first of all, what is image of T? So in option 2, what is image of T? Set of all y comma z such that y and z in R. This is the image, am I correct? Yeah?
Yes, ma'am.
Now you see that this is y times of 1, 1, 0 and 0 times of, sorry, z times of 0, 0, 1. Is it same as this? Yes or no? So now these forms the basis of image of T. So which is the same as image of basis of W. So this means image of T is same as W. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay, so this means that T is onto. Okay, so the other
One
result,
method is of kernel by kernel, and the second one is by basis, right, ma'am?
yes.
Ma'am,
Onto.
how basis of W
Agree.
is 110 and 001? W is the R square.
I have already written why the base is 110 and 001 for W. So for W, this is a set you
Okay,
are with.
okay. Thank
Yeah.
you.
See, here there is one result which we are using. What is that result? If dimension of, let's say T is from V to W, okay, and if dimension of V is equal to dimension of W, then T is 1 to 1. If and only if, can you complete the statement? T is
Not kernel.
T is 0.
no, yes, on to. Okay, so if dimensions are same, then 1 to 1 implies onto and onto implies 1 to 1. So here we have just shown onto, and since already we have proved dimensions are same, onto implies 1 to 1. So both 1 to 1 and onto, and hence T is an isomorphism. Okay, so here T is onto and the dimensions are same.
Two, right, ma'am?
Sorry, what?
The dimension is 2 for both V and
Yes,
W.
yes. Okay. So here we have dimensions are same and T is onto. So dimension of V equal to dimension of W and T is onto implies T is 1 to 1 and hence T is an isomorphism. So option 2 is an isomorphism. Which of the following is an isomorphism is the question. So option 2 is correct.
Mm.
You agree?
Ma'am, I have a
Ma'am,
small doubt.
Yeah.
ma'am, if
Uh,
x is 1 and y and z is taken as 0, then we get 0, 0, 0.
If X is
X is 1 and y and z is equal to 0,
mm,
then the image is 0, 0, 0.
1, 0, 0. Okay. Okay, here there is one thing I missed here. Here the thing is that the domain is from V, not from R2. So instead of 102, I don't know whether we should have considered 102 here. We should have considered some element from here which is non-zero. Here we need x is equal to y minus z. So maybe instead of this, if I have minus 1 here, it
Minus
will
1.
be z. Yeah, now is it fine?
Yes, ma'am.
Okay, now can you find something here in this format, x is equal to y minus z, and then you still have a non-zero vector where it is in kernel?
No, ma'am.
Yeah, it's a good question. Thank you, so that I understood the mistake I did here. Note that it is not just any vector in R3, it is a vector from V which satisfies this condition. Okay, good that you pointed it out. All right, now option 3. What is this transformation exactly? Can anyone say? This such a transformation is called the identity transformation, right? X going to X, Y going to Y, Z going to Z, right? So now if it is an identity transformation, both the domain and codomain should be actually same, right? So you are, first of all, in that case, can this element X comma Y comma Z first of all belong to W? So let me take 1, 0, minus 1. So you see that this is also 1, 0, minus 1. Does 1, 0, minus 1 belong to W?
No, ma'am.
no, ma'am.
It does not belong to W. So this means that this is not a, first of all, the transformation itself is not from V to W. Okay. So forget about isomorphism alone. This is not even a function from V to W. Okay. So we cannot consider this. Are all the options clear for everyone? Yeah.
Yes, ma'am. Ma'am, if it is from V to V, then it will be.
If it is from V to V, then it will make sense. Yes.
Okay, ma'am.
Yeah. Okay. So I don't want to do this problem again because it is of a very similar type. So I will leave it as a homework. Okay. So try this out because it is of the exact same type. So try this yourself. Okay. Fine. Consider the linear transformation T from R3 to R3 such that T of x comma y comma z equal to some transformation is given. Which of the following options are true about T? Okay. So in that case, we need to understand what does this transformation does. Okay. So how to understand this? So in that case, we need to understand what is the image. What is the relation between these three coordinates? Okay. So this is alpha. Let's call this as alpha, this as beta, and this as gamma. Okay. So now what is the relation between alpha, beta, gamma? Does this satisfy this relation is what we are going to check. Whether alpha is beta plus gamma, we are going to check. Can you all do the checking by yourself? Whether alpha and beta plus gamma are same, can you check?
Yes, I'm checking.
Yeah.
What we need to check, ma'am? Can you please once again say that?
Check whether alpha is same as beta plus gamma.
But why, ma'am, we are checking alpha equals to beta plus gamma?
Sorry, what?
As it is asked x equals to y plus z, that's why we are taking x as alpha, y as beta, and z as gamma. That's why
Yeah.
we are checking like that.
Yes, because we are representing any vector in range of t as x, y, z, and then we are having this condition here. And any vector in range of t is of this form. That's why.
Yes, ma'am. It satisfies this condition.
It satisfies this condition. So this is verified and hence you see that range of t is satisfying this condition. So option 1 is correct. Okay. What about the option 2? Do we have alpha is equal to 0? Obviously not, right? Obviously, we don't have any condition which says x minus y plus z is equal to 0. We don't have any such conditions given to us. Okay. And what about rank of t? So this is the range. If this is the range, then what is the dimension?
2.
2, right? Because you have set of all y plus z comma y comma z. So obviously, the dimension is 2. Is it clear for everyone why the dimension is 2? Yeah? All right. So rank is 2 and not 1.
Ma'am,
Okay.
in
Yeah.
option number 2, it can be satisfied when we put all the three variables equal to 0.
Yeah, only in that case it is 0, right? But here they are saying range contains only those vectors. But we have so many other vectors in range, right? So that is why it is not true. If they are saying range contains such vectors, then it is fine. But here they are saying range contains only these vectors. That is the problem. You understand?
Okay, ma'am.
Okay.
Yes, ma'am.
All right. Okay. So the next question is general understanding of rank nullity theorem. Okay, first of all, here they are talking about identity transformation. So you have a transformation from V to V where IV is equal to V. Okay, if IV is equal to V, you know that identity transformations are obviously isomorphisms, right? Identity transformations are obviously isomorphisms. So if they are isomorphisms, what do you know about the rank and nullity? So let's say that the dimension of V is n. So what can you say about rank and nullity of I?
Rank equals to n and nullity equals to 0.
Yeah. Okay. Now with this, let's try to answer. Nullity and rank of identity transformation on a vector space of dimension n are 0 and n respectively. Is that correct?
Yes, ma'am.
So if this is correct, then obviously option 2 and 3 are incorrect. Okay. Nullity and rank of an isomorphism between two vector spaces V and W, both of dimension. Now we are considering any isomorphism between V and W. Both are having dimension n. Now the rank and nullity, they are n and 0. Is that correct? Nullity is n and rank is 0. Is it possible?
No, ma'am.
Ma'am, can you explain why option 1 is correct, ma'am? Because I
Rank,
have forgot the reasoning, ma'am.
see, I have already written the answer here. For this transformation, rank is n and nullity is 0.
And why rank is n?
Why rank is n? Because it is an isomorphism. What about if it is an isomorphism? It is onto, right? If it is onto, you know that the image, so image of I is entire V, right? And so rank of I is nothing but dimension of image of I, and image of I is nothing but V, and dimension of V is n.
Okay, fine. Thank you.
And then by rank nullity theorem, you can say that nullity is 0. Or from isomorphism, it is 1 to 1 and hence nullity is 0. Okay, fine. Okay, rank and nullity should be 0 and n. The same scenario here also, so it should be 0 and n. Here they are saying there cannot exist an isomorphism between two vector spaces whose dimensions are not the same. So what do you say?
Yes, ma'am. Correct.
Correct. They are saying that cannot exist an isomorphism, which is correct. Okay, good. So, okay. Next, we are moving to what are inverse of a linear transformation. Now, consider a linear transformation T from R into Rn. When and how can we define the inverse of a linear transformation? So, before answering this question, tell me about when can we define inverse of a matrix. From there, we will come back here. So,
When
when can we
determinant is
say?
not equal to 0.
Yes. So A inverse exists if determinant of A is non-zero. Okay. So determinant of A is non-zero implies rank of A is equal to
Number of non-zero rows.
N.
n, because here A is an n by n matrix, right? We have T from Rn to Rn. So let's say A is an n by n matrix. So rank of A is equal to n. Okay, good. If rank of A is equal to n according to rank nullity theorem, what should be the nullity of A?
0.
0.
Okay. Now let's come back to the transformation. So from here, so let's say that you have a transformation, suppose where rank of T is equal to n and nullity of T is equal to 0. What does this say about the transformation T? This means that T is an, just now we saw,
Image.
Isomorphism. No.
so this means T is an isomorphism. So the answer is that, so when it will have a inverse, so T inverse exists if T is an isomorphism. Okay. And how can we define the inverse of a linear transformation? So here, how do we define a matrix which satisfies this condition? Is the inverse of the matrix, and then you have some formulas there. Same way, a matrix, a transformation which satisfies this condition. Here, this I is the identity transformation, is called the inverse of a linear transformation. Is that fine? Yeah.
Yes, ma'am.
Yes, ma'am.
And what is the matrix representation corresponding? How do we find T inverse? You don't have to find T inverse. Find A inverse. Where, so first, let's say that given T from Rn to Rn. How to find T inverse? Assuming determinant is non-zero. Okay. So let's say that here A is the matrix of T with respect to standard basis for both domain and codomain. Okay. So in that case, for finding T inverse X is A inverse X. That's all. You compute A inverse and then find A inverse X. That will give you T inverse X. Is that fine? Computing T inverse. Okay. If you know to compute A inverse, then you know how to compute T inverse. All right. Let T from R4 to R4 be a linear transformation. Suppose V1 and V2 are two distinct solutions of Tx is equal to 0. What is the maximum value that rank of T can take? Okay. First of all, tell me about the kernel. V1 and V2 are two distinct, maybe I will say two distinct, I should add non-zero solutions. Non-zero solutions of Tx is equal to 0. So you know that V1, V2 belongs to kernel of T and they are non-zero, right? So this means what should be the nullity? The nullity should be at least
1.
1 or 2. You have two vectors, two non-zero,
Okay. 2.
two non-zero, at least 2, right? It should be at least 2. It can be 2 or 3 or 4. So you know that the nullity plus rank should be
4.
4. And the rank and the nullity is minimum 2. So it can be 3 or 4 as well. So in those cases, what are the corresponding rank? 2,
1
2,
0.
1,
0.
0.
1, 0.
What is the maximum value that the rank can take?
2.
2.
The answer is 2. Okay. But there is one catch here. They are two distinct, but suppose V1 equal to alpha V2, then what happens?
Then ma'am, the answer will be 3. Right?
So they are just distinct. We don't know about linear independence. So in that case, here actually it is greater than or equal to 1.
Yes.
Right? So in that case, we should consider here 1, 2, 3, 4, not just 2, 3, 4. So if this is 1, then you know that this is 3. So the answer should be 3 here. Okay. So just we are given it, they are distinct, but linear independence are needed to talk about the dimension. So we can say that the nullity should be at least 1. It can be minimum 1. Because in this condition, the nullity can take the value of 1, even they are distinct. Okay.
How
Yeah.
are you
Ma'am,
taking nullity is greater than or equal to 1 or 2 or any other number?
Because see, kernel has V1 and V2, both are there in kernel. Now suppose V1 equal to alpha V2, in that case, both contributes to one vector in the basis of kernel. Right? It cannot be, both the vectors cannot be there in the basis of kernel. In that case, the nullity should be minimum 1. Agreed?
Kernel is the solution set, right?
Yes. Kernel and nullity both are same. We are talking about the dimension of kernel or the null space.
If it was three means V1, V2, and V3 belong to kernel, then the nullity would be greater than or equal to 3.
No, if even v1, v2, v3, even if you have three distinct vectors in Tx, still the minimum you should have the minimum dimension is 1. Okay.
No, not minimum dimension. I'm talking about my kernel space T has V1, V2, and V3 as the vectors. Then my nullity of T will be greater than or equal to 3, right?
Yeah, at least 1. No, not greater than or equal to 3. For example, let us
At
say
least
you,
at
yeah,
least one. Why, ma'am?
why? Because suppose let us say your V1 is 1000 and your V2 is 2000 and your V3 is 3000. And let us say V1, V2, V3 all belongs to kernel of T, right? Now, and in that case, what can you say? In the base is only one vector contributes. V1, V2, V3 are,
That's right. If they are multiples of each other, then it is greater than or equal to 1. But
yeah,
if they are not the multiples of each other, then greater than equal to 3, right?
that's why I'm saying the minimum is 1. We don't know whether they are multiples or not. So we consider all possible scenarios and take the case where it is the least, the minimum.
Okay,
Okay,
but
because
if it wasn't, if it was told that they are not the multiples of each other and they are non-zero solutions, then
yeah, then we can say that the nullity is here. For example, in this case, V1 and V2 are two linearly independent. Suppose they have given, then in that case, the nullity is greater than or equal to 2. Okay. All right. Okay. Now we are going to look at what are the steps involved in finding the null space and range. Okay, so straight away maybe I'll go to the problem. Usually I prefer that by doing a problem and then going back to that steps. So let us consider this transformation we are here. Find the basis for the null space and the range space. So the first step is always to find the matrix representation. Everyone, I'll just give you 2 minutes. Find the matrix representation of T with respect to the standard basis for both domain and codomain. So let's say that your V1, V2, V3, V4 or standard basis of R4. So find TV1, TV2, TV3, TV4 and find the matrix A.
Ma'am,
Yes,
A is 2468,
A is
2468, 1305, and 1163.
okay. Remember, this is TV1, TV2, TV3, TV4.
and
Okay.
I guess that should be not means row wise, that should be column wise.
See, this is your TV1, this is TV2, this is TV3, this is TV4. Is that correct? Yeah.
Yes, ma'am.
All right. So here, since I don't have much time, I'm going to straight away write the So here I will give you this as a homework to verify. I'm going to directly write the RREF form here of this matrix, which is 1, 0, 9, 2, 0, 1, minus 3, 1, 0, 0, 0, 0. So now for the first row, what is the pivot?
1.
This is the pivot.
Yes.
And second row, this is the pivot. And the columns containing
Pivot are the leading elements.
pivot are the first non-zero element in any row. Okay. And you see that only these two rows are having pivots, and it is in RREF form because you take the columns containing the pivots. Other than the pivots, there are no other non-zero elements. Hence, it is in RREF form. Okay. So the first step to find the basis for null space and range is first find the matrix of T with respect to the standard basis. Second step, find the RREF form of the matrix. Third step, figure out what are the pivot elements in the matrix. Okay. Now, once you have figured out the matrix, now your first observation is that see how many non-zero rows are there. How many non-zero rows are there?
2.
2. So you see that rank of T is 2. Okay. If rank is 2, nullity should be
1.
come on. The domain has dimension 4. So the nullity should be 2. Okay. So in the basis, we need two vectors, both in the null space and the range space. Now to find the basis of the null space, what we can do, let's call this matrix now as R. So this R x is equal to 0 will give you, so x1 plus 9x3 plus 2x4 equal to 0. Yes.
X2 minus 3x3 plus x4 is equal to 0.
Okay. Now we have to solve this. If we have to solve this, we have x1 equal to minus 9x3 minus 2x4 and x2 is equal to 3x3 minus x4. Okay. So in that case, we can express x1 and x2 in terms of x3 and x4. Okay. So x3 and x4 are the free variables here. Okay. So let's choose x3 as some t, t1 maybe, and x4 as some t2. So these are the free variables. The free variables contributes to nullity. Right? So you see that nullity is 2 here. And how are we going to figure out what's the null space? Null space of T is set of all x1, x2,
X1, X2.
maybe x1, x2 I'll write in terms of x3 and x4.
Minus 9t1 x3 minus 2 x4.
Yeah, I can write t1, t2. t1 minus 2 t2, comma 3 t1 minus
t2,
comma t1 minus
t1 t2.
t1 t2 in R. So now you know how to find the basis, right? So t1 times of, can you complete this? T1 times of
Minus 9
3
3
and
0.
1 comma 0
Yes, 1 comma 0.
minus 2 minus 1 0
1.
comma 1.
Okay, so you see that basis of null space of T are these two vectors.
Minus 9 3 1 0 minus 2 minus 1 0 1.
Okay, now how to find the basis for range? We can do it very directly. So here you see that these are the, look at the columns containing the pivot. Okay, So which columns contain the pivot? First column and
Second column.
so you choose the first and second column from the original matrix. Okay, so 2, 1, 1, 4, 3, 1. So basis of range of T. So columns of A containing pivot. What are they? 2, 1, 1 and 4, 3, 1. Okay. So what are the steps we have seen? First, find the matrix of A with respect to the standard basis for both domain and codomain. Second step, we find the RREF form of the matrix. Third step, find the solution of Rx equal to 0, and then from the solutions we can find the basis for the null space. So this is for the null space. Now for the range space, you look at the columns of R containing the pivot elements, and you choose the same columns of A from containing the pivot elements. That gives you the basis for the column space of A or the range space of T. Is that clear? So finding the basis for null space of T and range space of T, is that clear for everyone?
Yes, ma'am.
Okay, good. Okay.
Ma'am,
Yeah.
whenever we need to find out the basis, we need to apply the RREF form, and whenever we need to find out the span, then we need to find the linear combinations. Is that right?
Yes. So when
Okay.
you have to find this span, you need to look at the linear combination. Yes.
Okay, thank you.
Okay. So before that, what did you say? I did not listen to that completely. What was that previous before to span? What did you ask? I didn't.
I asked whenever we have to find out the basis, then
Hmm.
we need to do the RREF.
Yes, for null space. Yes, yes.
Okay.
For null space as well as for range. Yeah. So you all know that this is the rank nullity theorem for linear transformations, and this is the comparison with the matrix case. I have already given the explanation for this, right? So, and also this part I already told. So if T is injective, that is 1 to 1, then rank of T is the dimension of V. And if it is an isomorphism, you know the dimension of W and dimension of V are same, right? All right. So this also you all know, right? Because here, if it is 1 to 1, we know that kernel is 0. If kernel is 0, so 1 to 1 means kernel is 0. So if kernel is 0, nullity is 0. If nullity is 0, then rank is rank plus nullity is dimension of V, right?
Yes, sir.
And hence you have rank equal to dimension of V. Okay. And this part I already explained. Yeah. Okay. Now find the rank and nullity of the linear transformation and verify the rank nullity theorem. This is a very straightforward example. So here, what is the matrix representation for this? Whenever you have such a question, immediately look at the matrix. What is the matrix? What is T of 1, 0?
0, 0.
0, 1. What is T of 0, 1?
0, 0.
That's all. So now what is rank of T?
1,
And what is nullity of T?
1.
1,
1. So rank nullity theorem is this. Okay. Can there be a linear transformation such that the kernel and the image are same? What's your guess? Just say anything, yes or no.
Well, identity.
For identity, the range is R2 and the null space is just 0.
Okay.
Okay. Let's look at this example. What is a range? That X is in R. So basically, span of 0, 1. This is the basis. Now, what is the null space? 0, 0, 1, 0, x1, x2 equals 0, 0, which gives you x1 equal to 0. So, set of all 0, comma x2, x2 in R. Is this same as the range?
Yes, ma'am.
Yes,
Okay.
ma'am.
So, your null space is same as range. Yes, you have the previous example. Okay. Fine.
Remember, difference between range and kernel is the all the solutions of the homogeneous set of equations. No?
Yes. Okay.
And range is
Range is set of all tx such that x is in the domain. Please go back and look at the lecture. Okay.
okay.
We have covered range long back. Consider a linear transformation T from V to W such that dimension of V is equal to 5 and dimension of W is equal to 7. Okay. So in this case, you see that T is given to be 1 to 1. If T is 1 to 1, what do you know about the nullity?
Nullity is 0.
Yes. If T is 1 to 1, you know that nullity is 0. And then if nullity is 0, what can you say about the rank?
It is equal to the dimension of V.
Yes. So here this is 5 and this is 0. Is this fine for everyone? Yeah? Okay.
Yes, ma'am.
Now,
Ma'am,
yeah. So the next question, again here, it is given that dimension of V is 5, dimension of W is 3, and dimension of kernel of T is 2. Show that T is on 2. How can we show? If dimension of kernel, that is nullity, is 2, then what should be rank? 5 minus dimension of V minus nullity
Minus 3, ma'am.
3, which is dimension of,
W.
so T is on 2. Okay. All right. Can we find a linear transformation T from R4 to R3 with kernel 0?
We can, right?
Kernel 0 means what? Suppose, let us say, suppose kernel is 0. Then what does this mean? Nullity, it means T is 1 to 1. Right? If kernel is 0, then it means T is 1 to 1. So if, okay, so maybe we'll go it in the terms of nullity itself, that is better. So kernel 0 means nullity is 1. If nullity is 1, then rank should be
3.
3. But if rank is T, then T is on 2. Yeah? If T
Yes.
is on 2, then T is an isomorphism. But is it possible that T is an isomorphism?
No.
Not possible, because the dimensions of the domain and codomain are
Oh, no.
different. Okay, so this is of dimension 4 and this is of dimension 3. So they are not equal, and so we cannot have an isomorphism. So we cannot have a transformation T from R4 to R3 with kernel 0. Similarly, can we find a linear transformation T from R3 to R4 where range of T is equal to codomain of T? So that means we are saying that T is on 2 here actually. Is it possible?
No.
Again, why? If T is on 2, then it means what is rank of T? Rank of T is equal to?
Oh.
3.
3.
It's already given to, no, already it is given as 4.
Yes.
Yes, but it can rank be 4?
No.
No, not possible. Why it is not possible? We know that rank of any T where T is from Rm to Rn is less than or equal to minimum of m comma n. Right? So here minimum is 3. So rank is always less than or equal to 3 in this case. So hence it is not possible. So this is always a rule you should know. Okay. Okay. So we are almost at the end of the session. If T from V to W is a linear transformation and dimension of W is less than or equal to, just an observation from the last two questions. So if dimension of T W is less than or equal to dimension of V, just like in this case, then T cannot be
Isomorphism.
isomorphism, or first you can say 1 to 1.
1 to 1.
And then here in this case, if dimension of V is less than or equal to dimension of W, it cannot be
On to.
on. Okay. So there are two more questions. I guess these two questions maybe can be discussed in the TA session. So I have mainly covered all the important things. These two are just some exercises. So maybe we can cover this in the TA session. I can tell the TAs to cover these two questions. So I have covered all the important concepts to be covered in this topics given here. I hope this session was useful, and if you have doubts, please tell me.
Ma'am, can you give the link of your notes?
As usual, these
Ma'am, but for all the weeks, your notes are not there, ma'am. I want for all the weeks, actually.
my notes.
Yes, ma'am.
I'm not taking this session for all the weeks, right?
But, ma'am, your notes are detailed, and so it helps a lot, ma'am, actually.
Whatever sessions I'm taking, I'm providing the notes. Okay.
Ma'am, please provide the for other sessions also notes. If possible, ma'am.
Okay, I'm giving my notes of this session, and other sessions I have to look for the previous term and all. I'll see. Okay, otherwise you can always have, you can look at the playlist of the previous term. Yes,
Ma'am,
someone has.
yeah, ma'am, I'm seeing after seeing the playlist, na, the sessions you are not taking. So that is why I asked for notes.
Okay, okay, let me check that also. Yes,
Thank you.
some people have raised the hands. Yes, yes.
Ma'am, actually, I just wanted to ask, I'm an improvement student, but the thing is कि, whenever I am trying to open the note section, it is
Mm.
showing of the previous term, not of not of this terms from
I
last
guess
month.
you have to just click the current link. Can someone just give the correct link of the notes drive here so that she can access it? I guess she's looking at the wrong link. Yeah,
No, ma'am,
that is.
actually, I have taken that whatever you have said. I have taken a note of that before as well, but it didn't work.
It is not possible that if you click the current link, it will not work for you. So you have to just open with the IITM mail ID, then definitely it should work. Someone has shared the link, so please check now.
Okay, fine, ma'am.
Yeah, yeah. Other student, what's your question?
Ma'am, maybe I have just forgotten some things, but the question is dimension and rank of a linear transformation is same?
There is nothing called dimension of a linear transformation. You either have dimension of the domain or codomain. There is nothing called dimension of a linear transformation.
Okay, so the diamond. Okay, okay, ma'am. Okay, I got it now.
Okay, fine. All right, then thank you, and see you all in some other session then. Okay, thank you. Bye.
Ma'am,
Yes.
ma'am, I'm reminding you, ma'am, please kindly upload the notes, ma'am.